Okay, great. So we have started this part last time, which is the steady state stability, which is defined as the system after small and gradual change, the system will be back to its nominal operation or regain the synchronism. In this case, the system is stable or steady state stable. So this is of course different than transient stability. We will discuss it after that, inshallah, and also dynamic stability. Here, in a steady state stability, the system can be linearized around the operating condition, and we have zero input and zero state, and we will discuss both cases if we have neglecting the damping torque and swing equation, or considering the damping torque and swing equation. And we will define these time domain specifications for the time response. We will define what we call synchronizing power or torque coefficient, and also the natural frequency of oscillation, damping ratio of the response of the system, damped frequency of oscillation, which is omega d, natural and damped frequency. As we mentioned, this omega n has nothing to do with 60 hertz and 50 hertz. This is the oscillation of some mechanical quantities, which is delta and omega, related to mechanical part of the machine. So we expect omega to be within 0.6 to 18 radian per second, and also the frequency will be 0.1 to 3 hertz. This is the oscillation frequency, 0.1 to 3 hertz. Small disturbance means we can linearize, and this is the swing equation. We can replace just omega s by 2 by f, so it becomes equal to this. And this, of course, for 60 hertz or 50 hertz, you can substitute. And for zero input response, neglecting zero input, معناها delta B equal to 0. What is the input that we have in this swing equation? What is the input?
PM.
It is PM. So mechanical power input. So if we neglect the torque, damping torque, so this term is neglected here, and we can linearize the swing equation around the initial operating point, delta 0, and by considering a small change, delta, so we can replace delta by delta 0 plus delta in this equation, and sin delta also can expand it, and we did this already in last class, and we can have such approximation of sin delta. If delta approaches 0, then sin delta approaches delta, and this cosine delta approaches 1. So with this all simplification, we can end up with what? With this equation. So we can define now B max cosine delta 0. We'll define it as the synchronizing torque or synchronizing power coefficient, and the physical meaning of this BS is the tangent of the power delta curve. So this is the slope of the curve at any operating point. So in this case, we can say, if BS is positive, then the system will be stable If Bs is negative, then the system will be unstable. Let me bring the this okay here. So okay, so the slope here of this curve up to 90 degrees, the slope is positive, which is the power coefficient, and you can replace this part, which is B max cosine delta by Bs here. So now this is the linearize the differential equation. So we can have, in order to check whether the system is stable or not, so we can get the characteristic equation, we can get the roots or the eigenvalues. So we can convert it to S domain, so it becomes S squared delta delta. And of course, you can have this coefficient equal to 1 by multiplying and dividing. So at the end, you can have this equation, S squared equal to minus by F0 H over H times Bs. So these are the characteristic equation. So the roots can be, if this is minus sign here, then you can have based on this Bs. If Bs is positive, then S square equal to plus minus J square root of this. If Bs is negative, if Bs is positive, then this minus will be minus plus minus J square root of this. If Bs is negative, that means this negative will be multiplied by this negative. So in this case, this will be a real quantity, positive, then you have S equal to plus minus square root of this value. So plus minus a real part here. This becomes a real part. There is no imaginary in this case. If Bs is negative. Okay. Right. If Bs is positive, we have the roots plus minus J square root of this. So you have the roots here on the imaginary x. If both poles or roots are in the imaginary x, so what do you think the response would be? شكل الريسبونس التايم دومين ريسبونس شكله يبقى ايه؟ What do you think?
It will oscillate.
It will oscillate. It will oscillate and the response would be as such. Continuous oscillation. There is no damping and oscillation is the same. Okay, so this is if Bs is positive. If Bs is negative, multiplied by negative, so this is a positive quantity. So you have S square equal to plus minus square root of this quantity. So where is the poles now? One negative and one positive. Plus minus a real quantity here. This is plus minus a real quantity. So plus 2 minus 2. So these are the poles or the roots. If this is the case, but what is the response? How the response would be if this is the case? The response is unstable. If this is the case. So we can say no, synchronizing power coefficient for the system to be stable, this coefficient must be positive, which is equivalent to the angle is less than or 90 degrees. They are the same. So this is the condition for the system stability. If this is negative, we have one root on the right-hand side and one on the left-hand side, and the response is exponentially increasing, and the stability is lost. And if Vs is positive, we have, that means no delta is less than or equal 90. We have two roots on the imaginary axis, and the response is oscillatory and undamped. There is no damping, and oscillation is constant. The overshoot is constant. There is no damping. With the natural frequency of oscillation given by omega n equal to this. Of course, if you have second order equation like this, you can put it in its standard form, which is S square plus 2 zeta omega n S plus omega n square equal to 0. This is a standard form of the second order system, characteristic equation of second order system. So this is the coefficient of S is 2 zeta omega n. The free term is omega n square, and the coefficient of S square equal to 1. So if you compare this with the previous one, you have here, if you multiply this by F0 and H here, you have S square plus this free term only by F0 and so on. So you can write here from the previous equation, you have S square plus BS here multiplied by F0 over H equal to 0. So if you compare this with this, so you can say omega n square equal to this. So omega n equal to square root of by F0 BS over H. This is omega n. And in this case, zeta equal to 0. In this case. Okay. So this is the omega n. As you can see, the oscillation frequency, natural frequency of oscillation depends on the operating point, where is the delta, and also the inertia of the machine. If the machine is very heavy, let us take the machine is very heavy. Very heavy means H is very high. What do you think the oscillation frequency? Definitely, the oscillation frequency will be very, very low. So this is the heavy machine. Actually, if you have infinite bus where H equal to infinity, so omega n equal to 0. So there is no oscillation for the infinite bus. For an infinite bus, I am represented by a generator, but the generator, there is no oscillation in this generator. This is very heavy and nothing can affect its performance. So this is H, and the synchronizing power coefficient, which is B max cosine delta 0. B max cosine delta 0. So if this is the case, you can see if delta 0 is low and delta 0 is high. If we are working at point A or point B, which one will give you like higher oscillation. What do you think? Are you, yes, Ahmed Suleiman?
Yes, Doctor. Point B.
Point B. Why?
Because
Yes.
Emacs.
Yes. And the machine is loaded, heavily loaded here. The machine here is heavily loaded. Here the machine is lightly loaded. Lightly loaded. فالoscillation يبقى ايه؟ يبقى higher يعني. Oscillation يبقى أعلى, light. The machine is light. But when the machine is heavily loaded, then you have the oscillation frequency is lower. طيب, okay. So it can be concluded that synchronizing power coefficient Bs must be positive, i.e. the derivative of the power angle curve is greater than 0. That means in the delta between 0 and 90 to avoid unstable response of the system. So what we want to emphasize here, the synchronizing power coefficient is an indication of the system stability. طيب, if we consider the damping torque, what do you think before starting analysis here? The picture will be better or worse if we have this term? If we don't have this term and the system is stable, we have these roots here. Okay, this is without our D equal to 0 here, without considering the damping. So the roots are on the imaginary axis, and the response is oscillatory. So assume that when we have a damping here, we consider the damping. Do you think the response would be better or worse? Ramadan.
I think it will be improved.
You are right. Since we have here extra damping, then the response will improve, and we expect in this case that these roots will move toward the left-hand side. If we have a damping coefficient here, we expect that these roots will be somewhere here on the left-hand side, and the response will be dampened. And you have here damped oscillation. The oscillation is dying out. Okay? So definitely considering damping will improve the response. But again, you can still express delta similar to what we have did before, delta 0 plus delta delta, and you can substitute over this swing equation and keep in your mind in d square delta 0 dt square equal to d mechanical minus similar to what we have done there. So we can replace, linearize the equation, and we can end up with this equation. So in terms of delta delta only, h over pi f0 d square and so on. So of course, to check the roots of this system, you can convert it to Laplace domain. You can take S transform or Laplace transform, and then you can write, of course, you can multiply by f0 over h, so it becomes s square plus d multiplied by f0 over h, s, d by dt will be s plus ds multiplied by pi f0 over h equal to 0. So this is the characteristic equation, and again we will compare it with the standard characteristic equation of the second order system, and we can find how much omega n, how much zeta in this case. So again, omega n is the same. Omega n is omega n square. We have here omega n square. So omega n square equal to this. So omega n equal to the square root of this. And you can substitute here 2 zeta omega n equal to d pi f0 over h. And you have omega n, and then you can substitute and you can get zeta for the system, the damping coefficient. So considering the damping, then we have multiply this by coefficient here. And the standard form of the second order system is as such. So if you can compare, then you can get omega n square natural frequency equal to the same as before. Natural frequency is not affected by the damping. This is natural frequency of the oscillation. So this is natural. So it will not be affected by the damping, and this is embedded characteristic of the system. This is an embedded characteristic of the system. So damping coefficient, as we mentioned, if you compare, then you can get 2 zeta omega n, and you replace omega n here. So you end up with this. And zeta equal to d over 2 square root of pi f0 over HBS, isn't it? And you have here 2 zeta omega n equal to this. Here 2 zeta omega n equal to pi f0 d over h. So you can have n here, and definitely you can end up with this equation. So of course, if d equal to 0, if there is no damping, then the zeta equal to 0, and we go back to the first case. But now let us study the h. As h increases here, and omega n and the zeta also decreases. Okay, and as you can see here, mathematically you can see, physically, or the physical meaning of this is that if you have a heavy machine, so the oscillation of the frequency of oscillation of this machine is very slow, and the response will be very slow in a heavy machine. It is not a light machine. You can have the oscillation as such, but this is a heavy machine. So the oscillation frequency will be lower, definitely. This is one. Second, the damping is very low also. If it is heavy machine, it's very difficult to damp it. And once it starts oscillating, it's very difficult to damp it, and it's very heavy. I will tell you, as you can see here from these mathematical expressions, if h increases, both omega n and zeta will decrease. As Bs increases, omega n will increase, definitely, as we mentioned earlier. And Bs increases, معناها انه الدلتا is what? delta is low. Delta is low. Okay. So this is B max cosine delta. So when we have BS increases, then that means that the delta is low. So you have here BS, then you can see the effect on omega n increases and the zeta decreases. Here you are, zeta damping on this, and this is, when you have BS small, then you have this again. You are considering BS increases. That means zeta is decreasing. So this is the case. If you have any question.
Yes, Doctor.
Yes, please.
The oscillation of small machine, for example, when the machine is now on load, maybe the generator is on load, the oscillation should decrease. Like, especially, I should expect that the oscillation of the machine, assuming it is heavily loaded. So how is this compared to a heavy machine that is not on load?
Here and here, A and B. At point B, the machine is heavily loaded. Am I right?
Yes.
A is lightly loaded. So what is your question now?
This machine is a light. I mean, when you say light machine, we are talking about a machine whose weight is high, is big.
The machine is, you mean H, the inertia of the machine?
Yes, the inertia of the machine.
What is your question now? Sorry, and I didn't get your point.
Yeah, okay. What I'm saying is that when we say heavy machine, we're saying the machine is heavy, and the mass of the machine, maybe the rotating wheel of the machine is big. So the machine has big inertia, and so the machine is heavy. This is one point. Then the second point is that if this machine is now on load, if the machine is subject to load, it has become loaded now. So how does the oscillation of that machine, like the curve you showed up, where we saw that the oscillation of a heavy machine is kind of slow. So what happens if this machine now become loaded, like being connected to load or something, as compared to a light machine that is
okay.
Yes.
Look at this. Look at this. Here.
Yes.
If the inertia increases, then omega n decreases. Let us put it here.
Yes.
If H increases, omega n decreases.
Yes.
طيب. If BS decreases, omega n also decreases. Right?
Yes.
BS decreases means what? BS decreases means what? Means no BS at point B is lower than BS at point A. And loading here, if BS decreases معناها ان الماشين is ايه؟ is heavily loaded. Right?
Okay.
يعني delta is ايه؟ increasing here. Right?
Okay.
So that means انه loading of the machine have the same or similar impact of H. And if you have a machine and you load it, that means you, as if you increase the inertia of the system. Am I
Okay.
right? Is it clear?
Yes. If machine, it's as if you increase the inertia of the system if it is loaded. This is the point I'm trying to understand. Okay, if the machine is a light machine originally, if it is not loaded, if it's a light machine,
Yeah.
it means that this machine is small and it's not heavy, so it does not have good inertia. So
By the way, I would like to emphasize on one point, Bas,
okay, doctor.
to avoid any confusion.
Okay.
Omega n increases or decreases, it doesn't matter, or it doesn't mean and the system becomes unstable or becomes stable.
Okay.
And when we say omega n is increases, معناها ان the system is not يعني approaching instability.
Okay.
This is depends on the oscillation frequency. It has nothing to do with the damping.
Okay.
The
Okay.
system is stable or unstable. This is the oscillation frequency of the response. Maybe this is the response, or this is the response. Could be also the response is very fast. Oscillation frequency is very fast, but the system is still stable.
Okay. Okay.
And it has nothing to do with the stability. When we say omega n decreases or omega n increases, it doesn't mean when the system becomes stable or unstable.
Okay.
It has nothing to do with that.
Okay.
Is it clear?
Yes. Yes. No. Clear.
Okay. Yani for the system of omega n could be, for example, as we mentioned, in omega n between our frequency of oscillation between 0.1 to 3 hertz. So this is could be or 1 radian per second. And another system you can have 18 radian per second. It doesn't mean this system is more stable than this system. Okay? It doesn't mean this system is more stable than this. Maybe if there is no damping for this system, this oscillation will increase very slow, but will increase with time, and the system becomes unstable again. And in natural frequency is doesn't indicate or doesn't carry any information about the stability. How much omega n, it doesn't reflect the stability in any way. Is it clear?
Yes, yes, doctor. Thank you.
Okay. We have another question, Hussein Ali.
Yes, doctor. Now, based on what you have just explained, now this the natural frequency is not affecting the stability. So, what is the information that we can get, technical information about the machine or the system from omega n? If it is too fast or too low, will it indicate anything? Either it is related to stability or related to something else, or just a specification for the machine?
Okay, so this is a good question. Omega n, we need to identify it, although it doesn't give us any indication about the stability, but we need to identify it. How much the omega n or the system, if we have any oscillation or any disturbance. Why? Why do we need this piece of information? Later, we have an oscillation like this, okay? And we need to design a controller in order to enhance the system stability. So we have to have this frequency in order to design our controller to respond or to give the maximum response at this oscillation frequency. Is it clear? I mean, if you have any controller like lead lag controller KC 1 ST 1 over 1 plus ST2 مثلا, and just a lead lag stabilizer, which is most widely used or widely used in utilities. And so far they are having this kind of stabilizers, which is a lead lag stabilizer. You can have one block, or you can have another block, 1 plus ST3 over 1 plus ST4. So when you want to design this controller, you need this controller to respond, to give you the phase margin and the gain margin at this oscillation frequency. And you can substitute here S equal to J omega N in order to design the time constants T1 and T2. You need to find how much the phase angle of this block at this oscillation frequency. So it doesn't indicate any information about the stability, but we need this in controller design later on to enhance the system stability. We need to design the controller to respond at this oscillation frequency with the phase lead that we need to compensate the phase lag, as we will discuss this in more details at the end, toward the end of the course. So we need this omega n. Did I answer your question?
Yes, doctor, yes.
Okay.
Thank you.
Thanks. Okay. Okay. So the characteristic equation of this second order system, which is S squared to zeta omega ns plus omega n square, for normal operation, zeta is less than 1, which the system is overdamped. We call it overdamped response. And the roots are, for this equation, definitely the roots equal to minus p plus minus square root of b square minus 4ac over 2a. So you can substitute here and you can get the roots, which is minus zeta omega n plus as such. So you can say in S1 and S2 equal to, we have a real part here. This real part we can call it sigma and the j omega. And this omega d, this is the damped frequency of oscillation, omega d, which is equal to omega n square root of 1 minus zeta square. If zeta equal to 0, you have nature of frequency, there is no damping, so both frequencies are the same. So omega d is the damped frequency of oscillation, which is omega n square root of 1 minus zeta square. Okay? It's clear that for positive damping, for this zeta, if zeta is positive, omega n is positive, definitely omega n is positive quantity, and they will represent the frequency. 1 hertz, 2 hertz, 3 hertz, but this is a positive quantity. So if zeta is positive, that means you know the real part of this root at the left hand side, if zeta is positive. So the real part here is negative, and the roots are on left hand side. This is zeta greater than 0. Okay, and the system here becomes stable, and the oscillation here becomes damped oscillation. If zeta is negative, definitely this part will be positive, and the zeta is negative, معناها ان the damping is negative, damping is negative معناها نفي إثبات. يعني damping is negative معناها إنه السيستم is as a negative damping, or the system becomes unstable. So we have here zeta is greater than zero, less than zero. System becomes unstable. Okay, I hope you know these things are easy to understand. It's clear that for positive damping, roots have negative real parts, and if the synchronizing bar coefficient is if the synchronizing bar coefficient is positive, yes, the response is bounded, and the system is stable, as we see in the time response. If we have the poles or the roots are on the left-hand side. For possible extension to multi-machine system, usually we use the matrix form. We put the characteristic equation in matrix format or in state space form. As we mentioned earlier, with this characteristic equation, you can write it in two first order differential equations. You can say this is d omega by dt, and then you have d omega by dt as a function of omega minus omega steady state. And this is we already, when we talk about the swing equation, we already pointed out there, and we can write the swing equation in two first order differential equations. So we can define here x1 equal to delta delta. In this case, x2 equal to x1 dot, which is delta delta dot. And the swing equation, we have the omega dot. The swing equation or delta double dot. So we can write here the x1 dot equal to x2 and x2 dot equal to delta delta double dot, which is equal to this. And in matrix form, you can write x1 dot and x2 dot, or in compact format, x dot equal to x of t. Is it clear? So this is the this is the state matrix A, and you have here this is delta omega dot, and this is delta delta dot. This is the unforced state variable equation. If the state variable x1 and x2 are the desired response, we can define, if you want to observe x1 and x2, you can define this as your output. So you can define y of t equal to x1, y of t equal to x1 and x2. So we have this identity matrix, and then you can derive the characteristic equation Si minus A inverse, taking the Laplace transform. So you can write S of x of S 160 over equal to A x of S, or x of S response in S domain equal to this, and x0, this is the initial condition. And then you can take the inverse Laplace transform to find out the time domain expression for delta of t and omega of t. These are the states here for the this representation. Are you following, Shabab? If you have
Yes,
any question, please ask. So Si minus A equal to, you have this Si minus A, and then you can substitute x of S equal to this is the characteristic equation, and then you have x of 0. So you can write x1 and x2 equal to this over the denominator x2 also equal to minus omega n. طبعا we have here x1 x2 يعني x0 دي برضه هي vector which is x1 of 0 x2 of 0. Okay, so you can write x2 equal to minus omega n square x1 sx2 over this. Okay, when the rotor is suddenly perturbed by a small angle delta zero, delta zero, if we have any change in delta zero, what is the initial value of delta omega zero? The initial value of delta omega zero here is 0. Why 0? And usually the machine at the operating condition, state operating condition, operates at synchronous speed, omega s. Omega equal to omega s, omega 0 equal to omega s. Okay, so the deviation in omega equal to 0. So omega minus omega s equal to 0. This is delta omega equal to 0, delta omega 0. So usually the speed, the initial speed omega 0, you can put it equal to omega s in radian per second. You can put it as 1 per unit. So that means on the rated speed. So sometimes we express delta omega in per unit, not in radian. So in radian per second, it is equal to 377 for 60 hertz system, and the 314 for 50 hertz system. So these are the initial conditions. We have initial step in state, 0 input response. We have initial change in the state, but there is no change in the input. So we have delta 0 and delta omega 0 equal to 0 here. So you can get delta of s, which is here, equal to this multiplied by delta 0 and 0 over this. So this is delta of s, and delta omega of s equal to minus omega n squared times this, and the of s times 0 over this. So this is the delta omega of s. If you have such equation in S domain, can you get the inverse Laplace transform in order to get delta of t or delta of t and delta omega of t? And of course, you can easily get inverse Laplace transform. Taking the inverse Laplace transform results in 0 input response. This would be delta of t as a function of time, equal to the initial change in angle, square root of 1 minus zeta square, e to the minus zeta omega n t sine omega d times t plus theta. So of course you can, with time, you can get how much delta of t. And also you can do the same for delta omega of t by taking the inverse Laplace transform, and you have it as such. Okay. Of course, you can definitely theta equal to cosine inverse zeta. As we mentioned earlier, we have if you have a bool here, so this is sigma. This is omega d, and this is omega n. And you have here cosine theta, zeta equal to cosine theta. So theta is defined as cosine inverse zeta. Therefore, the motion of the rotor relative to the synchronously revolving speed field is, of course, this is delta delta. This is a change in the angle. If you add the change in the angle and with delta 0, you get, of course, the total angle. And also for the same here, you can have steady state omega s, and you can add it to delta omega of t to get the speed of the machine. Omega s plus omega s, which is omega 0. Omega s equal to omega 0, as we mentioned earlier, plus delta omega of t. So you can have it here. So this is also omega s, synchronous speed. So these are delta of t and omega of t for the system zero input response. Of course, the response time constant, usually we have this real part of the eigenvalue. You can say no tau, time constant of the response, equal to 1 over the real part of the eigenvalue. So 1 over sigma, the eigenvalue is written as sigma plus j omega. So you can have 1 over sigma. This represents the time constant of the. We have zeta already in terms of the h and the d and so on, and you have omega n. So you can write 1 over zeta, 1 over time constant of the system response will be equal to 2h over pi of 0d. This is the time constant. As you know, with the you can say how much is the settling time. This is some kind of characteristic of the time domain response. The settling time. If you are given here a tau equal to a certain value, so what is the relation between the settling time and the time constant? Let me ask first, what is the settling time? What is the definition of the settling time? Hussein Ali?
This is the time that the machine takes to reach again to its stable steady state condition.
Yeah, it needs some fine tuning. This definition needs fine tuning. Can anybody tell us, Ramadan Ali?
Yes, I think it's like a couple of cycles after the overshoot.
Again, it needs tuning here. Ahmed Suleiman?
The time machine stop, I think.
Completely stop?
To some percent, I don't think it completely stopped.
To some percent. Assume that this is the steady state value. You can take plus minus 5%. This is 1, this is 0.95, this is 1.05. So if the response comes to this region and stay there, then the time elapsed is the settling time. So assume that the system comes from here, go up, down, and then comes here. So at this point, at this time, the response comes very close to the steady state, within plus minus 5% and stay there. So this is a settling time. settling time, the response, when it reaches the region 0.95 and 1.05 plus minus 5% of the steady state and stay within these bounds. Okay, so this is the settling time. يعني definitely the system خلاص يعني almost the oscillations are already dampened out and يعني so this is settling time. Usually settling time is almost 4 tau. The settling time is almost يعني as an approximation can be considered as 4 time constant. So this is the settling time. So you can say no if the settling time of the tau مثلا for example is 1 second, you can assume no TS is 4 seconds, the system will be at the steady state. And after 4 seconds, approximately, system after 4 seconds will be at steady state condition, which is very close to the this. So this is the settling time, and this is the time constant. So let us go to discuss the other case, which is the zero state, delta equal to 0, and delta B not equal to 0. Now we have a change in mechanical power. We have some change in mechanical power. Again, we can consider both cases, neglecting damping and considering damping torque. We have a quiz today, very short quiz, but the quiz definitely needs some calculation. And prepare a calculator يعني next to you to use in the quiz. What is this? So let me just open the suppose open okay. So neglecting the damping torque, this is one case to be considered, and also considering the damping torque, which is definitely more, system becomes more stable in this case. Okay. If the input, which is the mechanical power, is increased by a small amount of delta B, and you replace delta B mechanical or B mechanical by B mechanical 0 plus delta B. So you can write the equation here. If you go back to that equation where we have by H over by F0 d square delta by dt square equal to B mechanical minus P electrical, and B electrical, which is B max sine delta minus d delta by dt. What we will do here is we replace the B mechanical equal to B mechanical 0 plus delta B. Okay, so this is the initial value plus a step change here in mechanical power. So you just replace this delta B here by this value. So, and you can have this equation definitely, you have this equation now, which is the same. Delta delta will not change in any. This is B electrical, which is B max. You know, when you linearize this, it becomes Bs plus delta delta as we derived earlier. But we have here the additional part here, which is the change in mechanical power. Okay. So again, you can put this in the standard form of the second order system, and you can have s square plus z2 zeta omega n s plus omega n squared this, and in this case you can have this definition of omega n and zeta, and you can relate them with delta B. So if you multiply here by this coefficient in order to put it in standard form, where we have here the coefficient here is 1, so this becomes the equation. If you multiply by this coefficient, the standard form of the second order differential equation is known, which is this one. You have here the input delta U. Okay, so you can compare and you can say delta U equal to delta B, the change in mechanical power, multiplied by F0 over H. And you can define omega n square again equal to this value. And you can get also zeta here, which is the same expression as before, and omega n the same expression as before also. Do you have any question? Do you have any question? Okay, so I think you can start the quiz now for 5 minutes, and then we can come back after 5 minutes. Please. Do you see the quiz now?
Yes.
Okay, go ahead and oh, sorry, I didn't see the notification for prayer. We can catch the prayer after the class immediately, inshallah. Sorry for this. Okay, I think the time now is over. So let us continue. Again, the characteristic equation search for normal operation zeta is less than 1 and the roots are real part and the imaginary part. The imaginary part is omega d. Again, the same definition of zeta, omega n, omega d. All these are the same as before. This is omega d. And the characteristic equation can be written again in state space form. What we have an additional here, this delta u or delta b. We can define x1 dot equal to x2, x2 dot equal to delta double dot, which is equal to this. In matrix form, you can have this state space representation. You have here the A matrix, and you have here B matrix. Now we have B matrix, and we have an input here, which is delta U. And delta U is a function of delta B as we derived earlier. So this is the state space. Of course, you can write it x dot equal to x plus b bu, and where a and b equal to this, and you can get the transfer function or the characteristic equation, which is the determinant of the transfer function. If the state variables x1 and x2 are desired response, you want to observe x1 and x2, which is delta delta and delta omega. So you can define the output matrix y equal to the identity matrix of the x1 and x2. So you can write y equal to cx. If you take the Laplace transform, you can have x of s equal to si minus a inverse p delta u of s. And if you have a step change, by delta u of s equal to the step value, which is delta u over s. So delta u of s equal to delta u over s. You have a step change in the input. So this is the delta u. So you can have x of s equal to this multiplied by delta u over s, which is delta u of s. You just write the previous two equations here in matrix form. You just write these two equations in matrix form. So you can have this equation and you can of course write x1 of s and x2 of s. x1 of s equal to this term multiplied by 0, so it will go, and then we have 1 times 1 multiplied by delta u of s. So it is delta u of s over this. And x2 of s, which is delta omega, equal to minus omega squared times 0, so it will go, and we have s times 1 times this, so this s will go with this s. So you have only delta u over this. So what you have here, delta delta and delta omega, delta u over s, and the delta u only. So you can of course write delta delta of s equal to this over, and delta omega equal to delta u over this. And you can take inverse Laplace transform to get delta delta of t and delta omega of t. Same approach as we did before. This is delta u over the characteristic equation, and then you have delta omega of s equal to this. And if you take inverse Laplace transform, you end up with delta delta of t equal to the step change. How much the change in mechanical power? Come on, this is a function of mechanical power actually. This is by f0 over h times delta b. This delta u equal to this. So you can have omega n و zeta are of course, definitely calculated from the H synchronizing damping coefficient and all this, synchronizing power coefficient. And you have omega d also known, so you can, this is the time response. So as you can see here, if the system is stable and you have a damped response, so the response will, if you start here, if you are talking about delta omega or delta delta or delta delta, then you start from here, from 0. So this would be the response. If you are talking about omega and the delta, so you are talking about the initial values. So this is delta 0, and then you add to it delta delta. So this is delta of t now. Now delta delta, of course, definitely will start from 0, and at the beginning there is no shift in 0 state. It is 0 state. So you have delta omega of t as a function of t, and of course you can get delta delta of t and delta omega of t. This is the delta of t, and you can write also omega of t. So this will give you the response of the system if you have any change in mechanical power. So we replace delta u by its value, you can have this response. Again, response time constant, which is 1 over zeta omega n, equal to this, and the settling time is approximately 4 tau. So the system will be at steady state operating point after this amount of time. Do you have any question? Okay, so we have here an example. Which I think we have to stop here, and the time is over. So we will discuss this example later, inshallah. So, and I would like just to, regarding the term paper, and some of you, they are asking about what is left there. And already Al-Juhani selected one, Ayub Al-Khalifa selected one, Al-Hurani, Ahmad Al-Nas, Ma'ruf, and Sulaiman, Saad Al-Ahmad already selected one paper. So this is the remaining now. So these are the remaining papers. So I don't know whether do you see it clearly? Do you see the titles?
Yes, Doctor.
So you can select.
Actually, Doctor, I have sent to you. We have selected the impact of high renewable penetration on the power system operation mode, data driven.
This one?
Yes.
This one.
I don't see. Yes, the one.
Impact of high renewable penetration on the power system operation mode, a data-driven approach. Okay.
Yes.
This is already done. So, but you have to send it to me. And send to me.
I did.
طيب خلاص. Who else is still waiting for the selection? خلاص, and I don't want the people to send me and I send it back and this is booked. These are the remaining topics. So you can select from them now and tell me which one, so we can avoid any conflict. Ayub Al-Khalifa.
I have a small comment, Doctor.
Okay, go ahead.
Regarding to the quizzes.
Let me ask first the one who started the recording to stop recording. خلاص أنا already finished the material. So what is your question يا أيوب?